Okay, I just want to catch up on our particles and waves decay equations. So if we're going to look at the ways that nuclei can decay, which basically means lose energy, the first one is alpha decay. So it's Greek letter alpha. And you have a nucleus, its mass number will go down by 4, and its atomic number will go down by 2. That's to accommodate it losing 4 nucleons or protons or neutrons and 2 protons. So it's 2 neutrons and 2 protons, 4 in that column, and that's what we have. So an example of this was the one we had in the last video, which was thorium-90. 234 goes to 230 and becoming, is that radium? I wonder if I've written that right, whether it should be radium or whether it should be radon. I might have made a mistake there. And we've got 90 protons goes to 88 protons and 2. So you can see 88 plus 2 makes 90, 230 plus 4 makes 234. Our number of protons or neutrons are conserved, and that is our equation for alpha decay. Now, beta decay is, there are 2 types of beta decay, but we only do the one that's called beta negative. And in this one, a neutron becomes a proton. You might seem that seems a bit strange, but it is clearly a possibility as it's happening all the time around us. So, our neutron becomes a proton. What will that look like then? Well, if we do the same x goes to y type general equation, we've got our mass number. If one of our neutrons, which is normally hidden in this number of neutrons, this becomes a proton, it won't be obvious in this column because this is the number of protons and neutrons. So if you change, so that stays the same. So our mass number stays the same. And because one of the neutrons has now become a proton, this number goes up by 1. So that should be a plus 1. Now, we are emitting our electron, E minus, for beta minus decay. And you can't just generate leptons on one side of an equation. So there's a rule that we don't really do in detail about conservation rules. One of them is you can't have no leptons on this side and magically generate leptons on the other side. And if you do, you have to generate an equal number of anti-leptons. So basically, we've got our electron here, which is a lepton. And then we've got an anti, so the bar is for anti, electron neutrino. And because we've got an anti-neutrino, so we've got kind of in the lepton column, we've got, say, here we've essentially got plus 1 lepton and minus 1 lepton. So they sum to 0 leptons, which equals the number of leptons at the start. So anyway, so that's necessary, but these don't impact our numbers of protons and neutrons, which is the kind of question I'm thinking about here. So, carbon-14. So this happens all the time in everything that's got carbon in it, in you and in me and in the table and in the chairs and etc. etc. So anything that's dead is losing carbon. The carbon-14, it tends to be decaying. You're taking in carbon-14 in your food. So carbon-14 anyway. So the mass number stays the same. Carbon becomes nitrogen. We emit an electron, E minus, and we also have an anti-electron neutrino. So we've done alpha. That's beta. Gamma. That's it. Okay, what goes on with gamma? Well, gamma can basically be given is a kind of resorting out, changing of the energy states in a nucleus such that a gamma ray is emitted. So basically, a gamma ray doesn't have an equation. A gamma ray is just emitted without any specific change in the number of protons and neutrons in a particular isotope. Okay, so that's a quick one. We should have enough now to whistle through the course questions and also the multiple choice happy quiz.